Hello everybody, my name is Tefik. Today I'm going to speak about a follow-up topic to our casing proof of concept casing design video series. And before I go into the details, first of all I would like to pay my tribute to our great founder Mustafa Kemal Atatürk and his comrades and all the people have fallen into this soil for the existence of the Turkish Republic and for all the people who provided the or assisted in the rebirth of the nation. So, as you remember in our part number 5 video of the casing design proof of concept video series, we had basically a burst load case and a collapse load case. So today's discussion is about the burst load case. So that was basically the pressure or the load case of a frac shoe and full gas column to surface at a known specific gravity of gas. So we basically used a formula. If you remember, if you don't remember, please see the YouTube channel or the LinkedIn post, the original post for the link. In that formula, basically we have used a compressibility factor of 1. We basically considered the case as the ideal gas scenario, and with a known average temperature, basically we found the pressure at surface and also at each depth internal pressure profile by using the exponential function. So today I'm gonna basically get into more details in that equation. Where is that equation coming from? And also I would like to reiterate for compressibility factors for an average compressibility factor over a range, so that our pressure prediction is a bit more accurate than assuming as the ideal gas. So when we look at our wellbore schematic, so as we say, each company has a different set of load cases for burst, collapse, and axial. And in that example, the frac shoe minus or full gas to surface was considered as the burst load case. So you had the frac pressure, and basically you had a full column of gas extending to surface. So when you think about gas, it's a highly compressible fluid. So at every depth, you have a corresponding pressure, you have a corresponding temperature, and you have a corresponding compressibility factor, which is Z in a real gas case. And of course with a specific known specific gas gravity. So at every depth you have different ones, different values of the compressibility factor, because you have different pressures and temperature regimes. So you remember we basically solved the internal pressure of the gas by using an ideal gas, which is compressibility factor is equal to 1, and then we use the average temperature, and then by using the exponential function we came up pressure and internal pressure at each step. And when we use that internal pressure, of course we using the external pressure, and also we use that internal pressure as base of the ballooning force to compute for the difference in tension from the initial cemented base tension profile. So let's look at the real gas law first. So we know that it is basically pressure times volume is equal to compressibility factor times the mole of the gas and the gas constant and then the temperature. And we as drilling engineers, we tend to mix up the specific gravity of the gas with the liquids, and then we tend to basically use the specific gravity, and then multiply by 8.33 and then put in the hydrostatic equation. That's a very wrong thing to do, because the specific gravity of the gas is defined as the molecular weight of the gas defined by the molecular weight of air. Not like one Hg water is 8.33 ppg, and then we put in our famous hydrostatic equation to find the hydrostatic pressure. In this case, the gas specific gravity is molecular weight divided by the molecular weight of air, which is 29, mostly nitrogen. So it's kind of a ratio of the molecular weight of the gas, specific or rated to the molecular weight of air. So how we came to that exponential equation that we found in that part number 5 video. And again, for the video, please go to this one. I think I was showing the formula in that video as a formula. Now we're gonna prove it. So I would like to write the volume of the gas in terms of mass divided by the density of the gas. You remember, please don't mix up that specific gravity over here and then that's the density of the gas. As I said, for a gas, the conversion is not that straightforward, like the liquid, the mud waste we are talking about. So on the opposite side, I will need to write the number of moles basically by simply dividing mass to the molecular weight, and then I know that the molecular weight, because I was writing the specific gravity of the gas in terms of basically specific gravity of the gas, molecular weight of the gas divided by molecular weight of air. So I could write the molecular weight in terms of specific gravity of the gas times 29. So I write it here. I will carry to the final formula just to make it easier for us. So if you have a molecular weight, or if you have a specific gravity, which is basically molecular weight divided by the molecular weight of air, it's interchangeable to use. So if I basically organize the formulas again, I'm ending up with this density of the gas is simply equal to pressure times the specific gravity times 29, or I could simply say this as molecular weight. As I said, either way is correct. Depending on which is more practical to use. And then on the denominator we have the compressibility factor, we have the gas constant, and we have the temperature. So for the conversion of the units, if you use 2.77 at the denominator, which is basically I think is 80.275 or something, and then you had the 29. You had the 29 on the numerator. So if you take the R is equal to 80 something and then divide by 29, you end up with 2.77 on the denominator. And then if you use 2.77, and then if you use temperature in Rankine, which is Fahrenheit plus 460, if you remember your previous classes, then I will get a density of the gas in ppg, which I will be able to basically use the ppg in a known length of gas column to be able to come up with the pressure of that gas column, the hydrostatic of the gas column. So in this one, what I need to do is I go back to our initial hydrostatic equation. So if you remember, the hydrostatic equation is basically you integrate this part is also integration from D1 to D2, but for simplicity I keep it like this. But for P1 to P2, okay, you integrate 1 over density of the fluid, dP is equal to D1 minus D2, and then there's one here, there's a gravitational constant to convert from pound mass to pound force. So in our case we keep it simple as 1, because we will work in one units in SI unit. So that what happens is this raw fluid, if you think about our very simple hydrostatic equation of 0052 times density rho times the d1 minus d2 is equal to the the change in the hydrostatic pressure. It's the same equation basically. Raw fluid, because it's integrating with respect to dp, it basically comes out straight from the integration and then goes to the right hand side as a multiplication. So what we need to do is we take the raw fluid. We also already derived the raw gas here, so we will stick that raw gas into the raw fluid, and then as you know, there's a 1p over dp integration. So 1p over dp integration, 1 over x dx integration is coming up as ln x. If you remember, so ln x I need to integrate from ln x, I need to go from p1 to p2, so it will be ln p2 minus ln p1, and then if you remember from logarithm, so there's logarithm in the base of e, and then it is basically logarithm e, and then this difference could be written as p2 over p1 into logarithm e, or in the base of logarithm e, or ln p2 over p1, sorry. So on the right hand side, basically all these things, specific gravity of the gas 29, and again this is basically molecular weight. So I keep it like this, and then on top, on the numerator, you have the compressibility factor, gas constant, and the temperature. So here temperature is again in Rankine, so Fahrenheit plus 460, and then d1 minus d2, which is the difference in height. It will be in feet. So when you use the constants, correct units, you will end up with a 1545 at the denominator, okay, and you will basically get the ratio over here, and then this will be a number of basically a number. So this is dimensionless number. So you have the P2 over P1 is PSI or PSI. It will cancel, so it will be a dimensionless number over there as well. So what we have done is basically we again derive for the density of the gas, which is different from the liquid, all right, in terms of specific gravity of the gas, and then we have used the basic hydrostatic equation to be able to solve for the P1. In this case, let's because P2 over P1, you have a gas column, so let's say you have a pressure at the bottom. Let's call that P2, because the gas has kind of some hydrostatic component in it. The P1 will be less, so that's why you will have the P1 as the less in the denominator, and you will come up with a pressure difference in that column. Okay, so let's go to the second page. So simply I called the top part as x, if you remember on the first page, and then P2 over P1 is E, or we can call this as in Excel, if you want to do in Excel, is exponential E to the 29 times specific gravity of the gas. This is molecular weight, and then D2 minus D1 is the head difference, that's in feet, and then you have the Z in dimensionless number, and then T average is in Rankine. All right, so we basically derived this equation, right? But we have some issue over here, Z average. So how do we get this compressibility factor? You remember on the part number 5, we assumed 1 as a compressibility factor, which is an ideal case, which is an ideal gas case. But we know that because there is a compressibility factor, which is the V of a real gas. So on the first page, we defined as volume of the actual gas divided by the volume of ideal, because the ideal gas, there is no attraction between the molecules, or if it heats up, the volume is basically is not accounted correctly. We need to find the Z in the gas column, at least account for average compressibility factor with different pressures, so that we could account for a more accurate prediction of the pressure profile. I think at every point trying to compute the Z is might be difficult, require a good computing power, because compressibility factor will be itself also depending on the pressure and the temperature. So you need to start with some kind of a assumption to get into the iteration. I think there are some other methods like Redlich-Wong or the Peng-Robinson, but here I'm not going to touch base on that one. I'm gonna basically show or illustrate a simpler version of compressibility factor calculation or iteration that we could easily plug into an Excel spreadsheet. So how do we find the compressibility factor? So compressibility factor basically is depending on what we say is the gas gravity, pressure, and temperature. So there is in the literature there is a pseudo reduced temperature and pressure. Basically these are set in the literature so that each gas at the same pseudo reduced conditions will have the same compressibility factor, and then the critical pseudo critical properties can be estimated by I put the Sutton's relationship is in the literature as well. You could basically if you know the specific gravity of the gas, you will know the pseudo critical properties of the gas in terms of pressure and temperature. So I think there's a chart for petroleum engineers. I think you could remember this one. There's a standing and cuts graphs. If you remember, there are lots of lines populated here with pseudo reduced temperature lines and pseudo reduced temperature. If you remember, temperature of the gas divided by the pseudo critical temperature of the gas. So if you have the pressure, pseudo reduced pressure and the pseudo reduced temperature, you could basically read off the compressibility factor from a graph, which is okay. But for if you are looking for a profile of a pressure profile or to estimate the pressure profile in the gas column, for our burst load case, which is fracture pressure at the shoe, full gas to surface, or let's talk about a well controlled case where you have basically a known height of influx. Possibly you are looking into some methods that you could put in an Excel instead of reading off a chart, because reading it exactly to the 3-4 digit and then reiterating that to find another Z might be quite time consuming. So there's a method B which we could easily type into an Excel spreadsheet, is the Dranchuk Abou-Kassem relationship. So this one you could find in the literature as well. What they have done is they came up with a kind of a numerical solution where they basically fit the standing and cuts relationship into a formula extending from C1 to C4 with lot of coefficients. I didn't want to put all the formula here because it will consume a lot of space, but basically C1 to C4, they are constants which are basically depending on the pseudo reduced temperature and also reduced density. So reduced density is kind of a simple relationship between the pseudo reduced pressure and pseudo reduced temperature and a compressibility factor. So you see the dependency here. There's a Z to find the reduced density, and then we need to find that reduced density to be able to come up with a Z. So you notice that it's kind of an iterative format. So what we need to do is, so we use that equation, and then at the end you come up with this one, and then you will judge how close you are to the previous solution. So how we come up with kind of a iterative steps. So we have a pressure 2, let's say, and then we have a pressure 1 that we would like to find. Okay, that's the or another depth, let's say. Okay, that we need to find, and then what we need to do is, we have the specific gravity in the end. We need to start assuming a compressibility factor of 1. So we will start with an ideal gas scenario. Okay, so we will start with an ideal gas scenario over here. Start with 1. Okay, and then we start with 1, and then we will find another compressibility factor over here. So when we find that compressibility factor using this equation, all right, so we have 1. Okay, we have 1 over here, so we plug 1. This is exactly what we have done for the part number 5. However, more accurate way of reiterating for Z is gonna give better results for us. So that's why we are looking into this method B of Dranchuk Abou-Kassem method. So we have a Z number 1 here equal to 1, ideal gas. So we found the P2. All right. So we found the or P1 in this case, because P2 being the higher pressure. It's at in this case a fracture at 2 or a higher pressure. All right. So we found the P1, and then the next step will be P1 plus P2 divided by 2. So what I'm doing is, I'm doing kind of a midpoint, okay, and on the midpoint, and then I'm obtaining another pressure, which is the average of these two pressures. Remember, I'm trying to keep the temperature as temperature average over here, because you need to simplify the equation. Still, it will give you more accurate answers, but to find the temperature, you will need another significant amount of more iteration. So that's why I'm keeping the temperature as average. So now, then with P1 and P2, I obtain a new pressure, and then with that pressure, what I'm doing is, I'm putting into the Abou-Kassem relationship. I'm finding another PPR, a pseudo-reduced pressure, because I am now a new pressure. If you have a new perfect temperature profile, you could try to find the new pseudo-reduced temperature. However, as I mentioned, to simplify the iteration, I'm using the average temperature. But if you want to use the Neve temperature at the Neve depth, feel free to use. So with the Neve pressure, I obtain a Neve pseudo-reduced pressure, and then a Neve reduced density. So I plug into the Abou-Kassem relationship, all right, and then with the iteration, they were able to come up with. I think two or maybe 3 iterations. You will see that the compressibility factor is gonna basically converge to a number where you will see that your average Z on this interval, meaning on a column of gas, it will be similar to each other. So our purpose was to define as a average on this interval, and then you will basically come to this solution. So with that Z average, you can go you can put another calculation of you using the Z average, and then using the P2, you can come up with another P1. Or at every depth, that's 1545 over here. It's basically up there, and then at every depth, this was the head, you remember. So you have in this case, you have the casing shoe at 15,000 feet. So that was the originating pressure. So you have the 15,000 feet, and any depth above it, if it's surface, either at mud line or for a surface for surface stack, you will be able to put the D1 to your interest depth. So with that equation, with that z average, you will come up with a pressure at intermediate depth or at the surface. So let's go back to our example again. You remember it was the 0.55 Sg gas, and then we had the frac shoe in burst load case, and then the shoe was at 15,000 feet. We had the 11,177 psi. If you go back to the Excel video, you will see, you will remember what I mean. And then if you remember, we had our surface pressure at 34 psi, assuming Z as 1 as an ideal gas scenario. So if I use the Abou-Kassem relationship or correlation to finding the Z, and then if I follow this algorithm of finding a Z average over this interval, I could see that when I did the iterations, I can come up with a Z factor of 1.47 almost. So it's quite higher, almost 50% higher from the ideal gas case. Which basically, you look at the surface pressure, I'm obtaining around 9200 psi. So it's around 800 psi less than we have found out in that Excel spreadsheet using the same formula. However, using the compressibility factor of 1, which gives us underestimation of the pressures. So underestimation of the pressure, internal pressure, what does it mean to us? So you remember our design limit plot that we came up with. So we basically derived, you know, the burst uniaxial burst, and then uniaxial collapse, and then we also defined or derived the burst side of the triaxial ellipse and the collapse side of the triaxial ellipse, and then we also derived the tension and the compression design limit, and also we talk about the axes as being the delta P, differential pressure on the y-axis, and then on the x-axis is the basically axial stress plus the backup, which is internal pressure or external pressure, depending on you are looking at a burst load case or a collapse load case. So if I have a less internal pressure, which I have estimated using it as 1, what's going to happen is my delta P, if my load case is this squiggly line, because the delta P goes higher this way, there's a burst upper polygon is basically P internal minus P external, okay, or PE, let's call it internal minus P external. It will go up, and then also the second effect will be on ballooning. I have the initial tension profile. All right, now I have the ballooning because I have this load case. So what's going to happen is, if you remember that basically the formula that I have derived with the Poisson's ratio, and then the difference between the internal pressure, internal area, and the outer pressure and the external pressure, it will also drive the ballooning up. However, ballooning force up from as an additional tension from the initial cemented profile. However, because if it's above the cemented, let's say above the top of cemented, you remember we follow the kind of a midpoint approach, so it may be tuned above the top of cement. So in this video, what I wanted to show is to basically account for a compressibility factor, and then we showed how we basically came up with the equation that we have used on that video, and also we have talked about this Dranchuk and Abou-Kassem correlation of basically finding the Z or iterating for Z to be able to come up with a better pressure estimation. So the final word from me, ideal gas assumption, we need to take care with this one when we try to predict the pressure in the gas columns. Thank you for watching, and hope I will try to make another video hopefully for the heat tolerance. Thank you very much.